Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Welcome back, dear students. Hoping you all will be doing fine. As you know that in the two recorded lectures, we discuss two problems and we find the solutions using Gauss-Seidel method. So today we will start with another method, that is NewtonRaphson method of finding the solutions of power flow problems. So in today's lecture I will try to find a general form, or we will derive the general form of the NewtonRaphson method, and then in the other lectures we will discuss or we will try that method by doing exercises. So let me talk about this method, and then I will also talk about the general form of the Newton-Raphson method. So let's start with the discussion on the method, and also we will try to derive the general form of this method. So in today's lecture I will talk about the Newton-Raphson method. I will talk about the Newton-Raphson method, and I hope you remember I even mentioned in the class that all these methods of solving power flow problems are non-linear techniques, and even a given problem can be solved by these different methods. So the steps are different, but the end result could be even compared when the same problem is solved using, let's say, Gauss-Seidel and Newton-Raphson method. So one of the advantage of this method is that the steps that are let's say involved in converging or finding the solution are there are fewer number of steps, but this method converges faster compared to the Gauss-Seidel method. Although each step, when we will solve, you will see that each step is probably longer compared to the case of the Gauss-Seidel method. But anyhow, with fewer number of methods, the solution converges. The solution converges faster compared to the Gauss-Seidel method. So let me now talk about this method. So as you remember, in the beginning of the methods, we, let's say, make a guess. So what we do, we initially make a guess. So first we make a guess, and you know that solving power flow problem, the guess is either the angle. We have discussed it quite in detail before we even solved 3 problems using Gauss-Seidel method. So J is the it represents any bus, and depending on the number of buses in a particular problem, J may vary from, let's say, 1 to 2 or 3. So depending on the number of buses, if there are, let's say, 3 buses, so J vary from 1 to 3. And similarly, we guess, the other guess is the magnitude of the voltage that we guess. And you remember, the initial guess we represent with the 0. So this is basically the first guess, where we guess the value, and then based on the guess we determine the next values. So I mean this step is the same as either we make it in the Gauss-Seidel method or in the Newton-Raphson method. So J where J is equal to 1, 2, 3 and so on up to n, depending on the number of the buses in a particular problem or in a particular network. However, the difference between these two methods, if you remember in the Gauss-Seidel method, we put the initial guess and then we, determine the next steps based on the initial guess. But here, the slight difference or the difference is that as this is a guess, so obviously there is some error in the guess. So what we do actually in the Newton-Raphson method, we also determine the error in the first guess. So we make a guess and then we determine the error in this guess. So as I mentioned that we will in this particular lecture derive the general form of the Newton-Raphson method. So we will go through those steps. But the difference is that we make a guess and then we determine the error in this guess. So let's now what we do, we also determine the error. So we make a guess and then we determine the error in the guess. So determine the error, and we represent those error by this particular notation. This is the angle. So this is the first guess and this is the error in the first guess, and likewise the error in the voltage will be represented like that. U, which is the voltage, J, which represent any bus, and that will be the first guess. So this is these are the first estimates and these are the error in the first estimate. So now if we find, although as I mentioned in this particular method we will determine or we will derive the general form, and then using that general form we will find the error in the first guess. So and once we determine it, then we add it to the initial guess, and in that way we find the next estimate. So what we will do after we determine the general form, and then using that form we determine the error in the first guess, and if we add this error now, once we determine the error, we add it to the first guess, we get the next estimate. So what we do after finding the error, we add uj, this is the first estimate, plus this error in the first estimate, that will be added, and in this way we get the, so this is the next estimate, this will be the next estimate, and we represent this next estimate as you remember, this will be equal to, this next estimate will be equal to psi j1, we have already discussed. So this will be psi j1. So and similarly the case will also be similarly we can represent the voltage. So this is the guess, that is the guess, which is the magnitude of the voltage, that is the magnitude of the voltage, plus error in this first guess, which is delta uj 0. So that will, and remember this is not the power, I hope you remember we discussed it, this is not the power, this just represent the iterations. So these are the iterations. So this is the first guess that we represent with a 0, and then once we determine the error, although as I mentioned a couple of times that we have to use the general form of the Newton-Raphson method, so then we will know the error, and once we add that error to the first estimate, we get the next estimate. So this will be the next estimate, this will be the next estimate, and that will be equal to magnitude of the voltage at bus j So that will be the next estimate. So in this way, but obviously we guess the initial value, but all this method is to find the error in this first estimate. So how to find the error? The important thing is that how to find these errors. So now we will how to find these errors. That is important because we can make the initial guess. We know that in the flat start how we guess these values, but then the important question is regarding how to determine the error. So these are the error in the first estimate, and then now we will try to determine the general form of the Gauss-Seidel algorithm to find the error in the first estimate. And once we find that, we add it to the first estimate, and then we get the next estimate. So now let's talk about the general form of the Newton-Raphson method for determining these error in the first estimates. So let's proceed. So how to find the error? Now the question is how to find the error. Newton-Raphson method. We are talking about the Newton-Raphson method, and the question is now how to find the error. So we are talking about the Newton-Raphson method, and now the question is how to find the error. That we have already discussed how to find the error. So in the first estimate we have an error, and now we will derive the general form for determining those errors. So let's start with the power flow equation. Start with the power flow equations. Let me write it. Equations. Start with the power flow equations, and we have already discussed the different form of the power flow equations, in rectangular form, also in the polar form. So we have discussed those general form of the power flow equations even before. So for finding the error, we start with the power flow equations, and we know that the power flow equations can be written like that. Say the power flow equation. So the power at a particular bus k can be any value. That is equal to, we have already discussed these general forms, 1 to n y k j u k u j and cos of psi k minus psi j minus lambda j k. So this is the case. These are the form of the power flow equation when the admittances are given in the polar form. So when the admittances are given in the polar form, meaning to say that when the admittances are given in the polar form with a magnitude that is y k j e power j lambda kj. So once the admittances are given in the polar form, then the power flow equations are written in this format. So this is important that when the admittances are given in the polar form. Otherwise, if it is given in the let's say in the rectangular form, we know that the format or the shape of the expressions are different. So similarly, we can write the expression for the reactive power, that will be equal to Qk, which is the reactive power, that will be equal to, once again, summation j star from 1 to n, and n basically depends on the number of the buses in a particular network. So Now this expression will look like voltage at bus K, voltage at bus J, and the sign of the angles psi K minus psi J minus lambda Kj. So these are the two expression for the active and reactive power. I mean, once the admittances are given in the polar form. So these are the power flow equations. And as I mentioned even before that, we will follow all these steps to find the error. So the steps that we will follow is to find the error in the first estimate, because as I mentioned that once we find the error, we add it to the first estimate and we get the next estimate. So for finding the next estimate, it is important to find the error, and all these steps we will now discuss. All these steps are for finding the error in the first estimate. So now let's call the power flow equations. If we make a guess, because you know that in solving power flow problem initially we make a guess. So now if we make a guess of the voltage and that of the angle, so we called the power flow equation based on the guess, based on the initial guess. We call the power flow equation, or we represent the power flow equation, let's say based on the guess. Now let's call the power flow equations. Let's call the power flow equations based on the guess, based on the initial guess, based on the guess. Let's call the power flow equation based on the guess, and we know that the guess was, I mean, that of the angle. J could be any bus, depending, I mean, it could be bus 1, bus 2, bus 3, and similarly that of the voltage magnitude. So Uj, that is the, so let's call the power flow equations, because in these equations we might don't know the voltages and the angles on some buses. So for that we need to make the guess, and we call the power flow equation based on the guess as, so let's represent them as F P K and F Q K. So this is basically the power flow equation based on the guess of the voltage and the angle. So we represent them by FPK. So this is P is for the active power, and that is at any bus K, and similarly this is the reactive power expression based on the guess. So we represent them with FQK, and Q is the reactive power at any bus K. So let's now write the expression for FPK and FQK based on the guess. So now we can write like that. We can write the FPK and FQK. Let me write the expression for the FPK and FQK based on the guess. So I can write, once again, we are talking about the Newton-Raphson method. So let me put it on the top. So now based on the guess, we write the power flow equations, and we represent it with these two symbols or notations, whatever you call it. So now let me write the expression for the FPK and FQK. So now it will be FPK will be equal to FPK psi j, as this is the guess, plus the error in the guess. plus the error in this particular guess. So based on the estimate plus error in the estimate, we write the expression for the active and reactive power. So now the second guess is the voltage, so that is the voltage magnitude, that is the first guess, plus the error in this guess. So that will be equal to uj0. So this is the estimate of the angle and voltage, and these are the error in the angle in the first estimate, and that is the error in the voltage. So let's we call this equation as equation number 1. Similarly, we can write the expression for the reactive power, so that will become if qk will be equal to if qk with I mentioned that q is for the reactive power. So now let me write it like that. This is now the once again plus the error psi j0 and the magnitude of the voltage, the first guess, and the error in this particular guess. So we call it as equation number 2. So let's call as equation 1 and equation 2. Now as I mentioned that we will find the error because we are deriving or writing or discussing all these steps in order to find the error in the first estimate. So we have to find a general form of the Newton-Raphson method, and as I mentioned a couple of times that we make the initial guess, and then we have to find the error in that particular guess. So for that we are discussing all these steps, and I mentioned that we start with the power flow equations, and then we write the expression for the power flow equation based on the estimates. So these are the expression for the active and reactive power based on the estimates and the error in the estimates. So now let's take the Taylor expansion of these functions, because as I mentioned we will find the error. So these are the steps involved. Now let's take the Taylor expansion of these functions, because these are non-linear expressions. So now the next step is to take the Taylor expansion, because we are following all those steps to find a general form of the Newton-Raphson method for finding the error in the first estimate. So let's say now take the Taylor expansion. Take the Taylor expansion of these two functions. Take the Taylor expansions of these functions, But even before that, let me write the Taylor expansion for a non-linear function. So let's say, and we discussed that the power flow problem, it's a non-linear problem. We have discussed the non-linearity, and even I demonstrated the non-linearity to all of you in the lab. So now let's, even before writing before taking the Taylor expansion of these two expressions or functions, let me first write the general form of the Taylor expansion of a non-linear function. So let's say we have a non-linear function f of x. Let's say we have a non-linear function let's say we have a non-linear function f of x. So we have a non-linear function f of x, and let's say the this particular function have an exact solution. Let's say this non-linear function have an exact solution. So let's say this function f of x have an exact solution have an exact solution at x0 plus the error in this particular guess. So this is the guess and that is the error in the guess, and let's say once the error is added we get the exact solution of the nonlinear function f of x. So now if we take the Taylor expansion of the function of the nonlinear function f of x around x, so take the Taylor expansion of the function f of x. So Taylor expansion of Taylor expansion, first we write it for a nonlinear function f of x, and then we will with the help of that, once we know the general form, we will also write the Taylor expansion of the power flow equations. So Taylor expansion of f of x around the first estimate, that is this one. So the Taylor expansion of f of x around x is expressed like that. Let's say is expressed, so we will express it now. We will write the general form of it is expressed as, I hope you know it from your previous knowledge, that for this particular function f of x, the Taylor expansion can be written like that. So the Taylor expansion of the f of x around the first guess, so it can be written like that, plus the error in it can be written as f of x, this is the Taylor expansion of the function f of x around x, plus the derivative of f with respect to the x, this one, into the error in the first case, plus this is the, this is expressed in all these, all these are the expansion of the Taylor function involving all these terms, plus half of the second order derivative f delta and x0, and then delta x0 with a square of that, plus other terms. So now we are taking this is the Taylor expansion of a function f of x around x, and I mentioned that this function f of x is a nonlinear function, and we know that even the power flow problems, they are nonlinear by nature. So now first we write the general form of this function, and then by analogy we will write also the expressions or the expansion, the Taylor expansion. We will also take the Taylor expansion of the power flow equations based on the estimates. So this is the general form of the Taylor expansion of a function f of x around x. So it there are terms involved, so it is expressed with the help of these first three terms, let's say. So assuming now that the error in the first estimate, assuming that this error is quite small. So if this error is small, it means that then the higher order terms can be neglected. If the error is small, so then one can basically ignore the higher order terms. So ignoring the higher order terms, and let's say only taking the first two terms. So, but anyhow, even before that, let me now by analogy write the or take the Taylor expansion of the power flow equations. So now let's by analogy write the Taylor expansion of the power flow equation. So that would look like that. If we now take the Taylor expansion of the power flow equation, so it will look like that. That will look like this. So it will, if we take the Taylor expansion of these functions, we have written it, non-linear functions based on the estimate, so it will look like that. So the Taylor expansion of these two functions, and we have also now even I have written here the general form or the Taylor expansion of the function if of x around x. So now by analogy we can write the Taylor expansion, or we can take the Taylor expansion of the power flow equation. So let me now take the Taylor expansion of these two power flow equations. So the Taylor expansion would look like that, like it was involving this term, and then we have the derivative of the function with respect to x with the product of the error, and then we have other higher order terms are also involved. So now my analogy, the first term would become, knowing that we have the estimate and error in this estimate, and we have two parameters or variables involved. One is angle, one is voltage. So now the Taylor expansion of these two functions will look like that. This is now the Taylor expansion of the power flow equations. So it will look like that. It will have the this term. Likewise, we have here the first term. So now we have two variables. One is the angle, one is the voltage. So now it will look like that. You see, if PK, which is the active power, and the term similar to this one, with the two variables involved, one is angle, one is voltage, so it can be written like that. So that is the first term, because in the power flow equation you know that we need both the angles. We need, if we want to calculate the power flow, we should know the voltage magnitudes as well as the angles. We have discussed it before. So now in the power flow equation, two variables are involved. So now taking the Taylor expansion of these functions, the first term would look like that, and the second term similar we have here the derivative of the function with respect to the variable x, and then the product of the error is multiplied. So here we have now the derivative of the function with respect to the angle. J, as I mentioned before, J could be any value, 1, 2, 3, depending on the number of the buses in a particular network, and the product of the error is multiplied. So we will also have higher order terms like we have here, but now assuming that the error is small, we can ignore the higher order terms. So we are only taking the first two terms, this term and this term. We are ignoring the higher order terms because we are assuming that the error is small. So we are only confining the expansion to the first two terms. So otherwise, if one is interested, one can write even the higher order terms, but assuming that the error is small, so I believe even the first two terms would be enough. So similar, now we take the derivative of the function with respect to the voltage magnitude, and we multiply it with the error in the first estimate, and similarly the higher order terms can be written. So confining it only to the two terms, the expansion of the functions looks like that. Similarly, the expansion of the reactive power expression can be taken, and again involving the estimate and the error, and the estimate and the voltage magnitude and the error in that first estimate. So likewise, the Taylor expansion of the expression of the reactive power can be taken, and it looks like that. So this is now again, the same representation is the same, only difference is that here is the Taylor expansion of the active power and here it is the reactive power. Otherwise the rest it is the same. So now we have expressed, or we have taken now the Taylor expansion of these two functions, and it looks like that. So afterwards now we will also take some more steps to determine the general form. So now assume that after knowing the expansion, or which we confine only to two terms because of the assumption that the error is small. So now assume that we know the pk and qk on some buses, like on the load buses we know the value of the pk is any bus, q the reactive power at a particular bus. So on the load buses we know these two values. So assume that now the value of the active and the reactive power on some buses are known, and if we take that bus where both these are given, like on a load bus. So now, as I mentioned before, that the exact solution of a function f of x is when we make a guess and we find the error. So that will give us the exact solution. So now, as we have also represented the Taylor expansion, or we have taken the Taylor expansion of these two functions, where the assumption is involved, the first guess is involved, and also the calculation of the if we also take the error, so then it will be the exact solution. So now, as I mentioned, that let we now the active and the reactive power on some buses. So this will be the first term in both these expressions. This term, the first term in both these expressions. One is this term, one is this term, and one is this term. Because if you look to the even to the first terms, it involves the guess, and we make the guess in the beginning. So it involves the guess of the angle and that of the voltage, which we make in the beginning, and then we can find these terms based on our first guess. So now if we put it on the other side, because if the error is also involved, we will have an exact solution. And if pk and qk, let's say, they are now on some buses, likewise on the load buses. So now the first two terms in both these expressions, so the first two terms in both these expressions are the calculated active and reactive power based on the first estimate. So if we make a guess, we will calculate these two terms. Okay, so on the guess we will calculate these two terms, and if we subtract it from a known values, like on a load bus, we know these values. So if we now take the difference, that of a given value minus the first guess, it will give us the error in the first estimate. So the first two terms in both these expressions will be based on the estimates that we will make. We will calculate these values, and I mentioned that we will do exercise to make the steps more clear to you. So the calculation of the first two terms based on the guess, we can make the calculations, and then if we subtract it from a known values of the active and reactive power, like we know these values on the load bus, so we will get the error. So this will be the error in the first estimate, which meaning to say that now if we put all, if we brought it on the other side, so these terms will remain here, and the difference of these two we represent it with error. So now let me even write the expression for the error, because if we put it on the other side, these terms will remain here. So, and in that way, once again I repeat, we know the active and reactive power on some buses. So if we now put these terms, if we bring this term, the first estimate, if we bring it on this side, so we on this side the error remains, and it will be equal to a known value of the power and the first estimate. So that will be the error, and now the error will become, we can write now the expression for the error. It will become like that. So now these are basically the error between the real values and the estimated values. So these are the errors in the first estimate, and these errors delta p k0 and delta q k0 are the differences between the real values and the first estimates, the so-called power mismatches, because these are the errors. So these are in the power flow equations known as power mismatches. So now delta p k0, which is the the error in the first estimate of the active power and the error in the first estimate of the reactive power. So now once we move the first terms on the other side, the remaining terms are these terms, and the difference of these two is represented by the errors, which are the errors in the first estimate. So now these terms will remain on the other side, which are these terms, the same exactly these terms. So now we, as I mentioned in the beginning, that we have to find the error. How to find the error? This was basically, we, as I mentioned, that we have to find the error. So how to calculate the error? So we will find, basically, as I mentioned, we make up guess, but then all these steps are for finding the error in the first estimate. So now these errors can be written like that. Now these errors can be written like that, and in the matrix form, it can be even arranged like that. These are quite many terms, so I hope it is clear to you. So now these are the errors or the power mismatches in the first estimate. I have discussed about these two terms, and if we write them in the matrix form, the representation will look like that. And I mentioned that we ignore the higher order terms because we assume that the error in the first estimate is small. So now these expressions can be written in the matrix form like that. Now I can even write. I hope this. Let me write these two expressions. Few terms of that. Few terms of these, so to make it clear to you. So let me write few terms right in the matrix form. So on the left side we have the error, and on the right side we have these expressions, and to, let's say, I believe let me even discuss it here rather than writing, because it will take then longer time. So now we can write, because we know K can be any bus, and similarly J can be any value. So let's we start with the K equal to 1, and we know that for any value of K, J may vary from 1 to n. So if I take K, let's say if I take K equal to 1, and J will vary from 1 to, so K, let's say we now take K equal to 1, and we know that for any value of K, J will vary from 1 to up to n. So if we take, let's say, only the first case, K equal to 1, so this will become delta P1 0, and in the matrix form it will become, you see, the derivative of this function, K is 1, P is the active power, and J vary from 1 to n depending on how many buses we have in a particular network. So that will be then 1, and similarly we have another terms. We will have another term. This will be equal to delta Fp1 delta psi 2, and then delta psi 3. So, and similarly up to psi n. So for a particular K, we vary J from 1 to n, and we now, all these steps. So we know the calculation. We know from the calculation from the Gauss-Seidel methods that we, for any value of K, we basically vary J from 1 to n. So this will be now the derivative of the function with respect to the angle or with respect to the angles, depending on how many buses we have, and this is the derivative of the same function with respect to the voltage magnitude. Likewise, now we have the derivative of the function with respect to the magnitude of the voltage. So j once again vary from 1 to n. So now we likewise we discuss the angle. Similar will be the case of the voltage. And on this side we have the error in the angle psi 1. So similarly we take then k equal to 2, so then we take k equal to 3, and so on. K may vary from 1 to n, and for each value of k we vary j from 1 to n. So now there could be many other terms depending on how many buses we have. So now it is the general form where we have the derivative of the function, and we now take the k equal to n. So, and we similarly for even for k equal to n we vary the j from 1 to n. So this is now on the top left side we have the derivative of the function with respect to the angle. Now we take the derivative of the function with respect to the voltage, and this one, the down these terms, they represent the derivative of the function, but that of the therefore the reactive power from 1 to let's say the n terms. And then here we have psi 1, psi 2. So I mean these terms are exactly the same. Here we have it for the active power, here we have it for the reactive power. Similarly, here we have the derivative of the function with respect to the voltage, and here it is the derivative of the function, but that for the reactive power with respect to the voltage. So now we represent basically these expression in the matrix form. So I hope after this discussion this representation is now clear to you. So let me now talk about the other steps. So even now we can write this general form or this matrix form in a compact form. So the compact form of this matrix representation will look like that. And once again, to mention here that we ignore the higher order terms. Otherwise, then it would be the square of those terms would be involved. So we ignore that the higher terms, assuming or accounting for the fact that we make an assumption that the error is small. So we ignore the higher order terms. So now I will write the compact form of this matrix. So let me write now the compact form of this matrix. So it will look like that. So Newton-Raphson method, and I will write now this matrix, this particular matrix in the compact form. So in compact form, it can be written like that: delta U, this is rho, equal to J delta X rho. You know, we discussed it even before. Rho is the iteration basically. So rho, this represents the iteration. Now, if one look here, this is the, I mean, if I put it both, I hope, let me make it a bit down or maybe even up. So now if I, let's say, I mean, if we now, so, or maybe I can put it like that. So I hope now, yeah, I think this would be better way. So now this is the compact form of the matrix representation, where this one represents the error. This represents the error. This matrix we called it Jacobian matrix. So this J, which is this matrix, it is, we represented this basically is the Jacobian matrix. Jacobian matrix. And this one, as we know, these are the error in the angle and in the voltage. So these are the errors. These are the errors in voltage magnitude and angle. So this is now the compact form. This is now the compact representation or compact form of the matrix representation of the Jacobian, let's say, algorithm or method, whatever you call it. So now let me now talk about the last steps. So now because I mentioned that, if you remember, we discussed that I have to find the error. So how to find the error? And in this compact form, this represents the error. So now I can write like that, right? How to find the error? Now, because we will calculate the Jacobian matrix also based on the based on the difference between the noun values, on the load buses and the value that we will calculate based on the estimate. We will also determine the error, what we call the power mismatches. So we will determine the error that we calculate, which is the difference between the noun value and the first estimate. We will also determine the Jacobian matrix, and if we know the two values, one can determine the error. So now the error would become, the error can be calculated like that. So the error in the voltage and in the angle will be equal to the inverse of the Jacobian matrix into the power mismatch. Now we will let's say, as we know that in a power flow problem we make initial guess, and for that guess the rho will be equal to, so for the initial guess, let me put it here, for the initial guess the rho will be equal to 0, and then the error in the first estimate will be calculated. So based on the first estimate we will determine the power mismatches and also the Jacobian matrix, and once we know, we can determine the error in the first estimate of the angle and the voltage. And then once we know the error in the first estimate, so if we know the error in the first estimate, in the first estimate, let's say, what we will get the next estimate. So then psi j1 will be equal to psi j0 plus the error, which is the error in the angle. So in this way we will get the next, so this will be the next estimate now. So this will be the next estimate, and similarly we can write it for the voltage magnitude. So uj1 will be equal to uj plus the error in the first estimate. So in this way we will find the error. So some observations basically that I would like to discuss, that if one look to the Jacobian matrix itself, it has 2n, because these are the n terms, and then we have another n terms here, and similarly we have n terms and then n terms. So this matrix is basically 2n cross 2n matrix. So this is 2n cross 2n matrix. So it will contain 2n cross 2n elements. The Jacobian matrix contains 2n cross 2n elements. Also, we know that on the slag bus, because I mentioned that this method involved the calculation of the power mismatches, because for knowing these errors, we should know the power mismatches. And we know that it is equal to the known value minus the first estimate. But we don't know the active and reactive power on the slack bus. So for the slack bus, we don't know the value of the so for the slack bus, we don't know the value of the active and the reactive power. So here the active and the reactive power is not specified. Meaning to say that we will not be able to find the error. So these terms, because and also we know the slack bus is usually taken as bus number 1. So these terms will be removed from the matrix involving psi 1 and u1, because we don't know the value of the active and reactive power on the slack bus. So we will remove some terms, and I mentioned that we will learn this method, and we will also discuss that which terms will be removed from the matrix depending on the given parameters, and knowing the values on the different types of buses, like on the slack bus, voltage control bus, and the load bus. So this matrix will be reduced to some particular number of elements, but we will discuss that also. So we will learn this method by doing exercises. So, and even I mentioned when I discussed the general form of the Gauss-Seidel algorithm that we will learn this method by doing exercises, and once we did it, I hope you understand that method. So we have now in this method derived the general form of the Newton-Raphson method, and let me conclude my lecture. So let me conclude my lecture. So we talked about the Newton-Raphson method. And let me conclude. So conclusion, or let me quickly revise the steps. So what we do actually, we likewise in a power flow problem, we make a guess. And you know that in the flash start what values we assign to these variables. Now the next step is to find the error in these first guess, and for finding that error we have discussed all the steps, that we write the general form of the power flow equations, and then we, based on the estimates, based on the first guess, we write the power flow equations, and we represent them with these two notations. So based on the guess, we basically express the power flow equations, and we discuss those equations, that based on the guess we write basically the power flow equations, and then we take the Taylor expansion of these two expressions, and we discuss that once we take the Taylor expansion, then these terms looks like that. And we know that in the first guess we assign the values to the two variables. So we will calculate this, or we will calculate the first terms in these expansions. So also knowing that the active and reactive power is given on the load buses, we make a difference of the two and we get the error, what we call power mismatch. And now putting these two terms on the other side, the remaining terms will be equal to the error, or what we call the power mismatches. So that would be equal to then all these terms, and we once again, as I mentioned a couple of times, that we assume that the error is small, so we ignore the higher order terms. So these are the power mismatches, and these power mismatches then are written in the matrix form involving a 2n cross 2n elements. These are the errors, or these are basically the power mismatches. This is the Jacobian matrix, and that is the error in the estimates, angle and voltage, and we ignore the higher order terms. So as I mentioned in the beginning, that we make a guess and then we have to find the error, and this is now the algorithm or the general form from which we will find the error in the first estimate. So in the compact form, we even wrote those expression also in the compact form, and I mentioned that in the compact form it is equal to this one. This is the power mismatch, that is the Jacobian matrix, and that is the error. So now to find the error, because we will know the power mismatch, we will also calculate the Jacobian matrix, and from that we take the inverse of the Jacobian matrix and we multiply it with the power mismatch and we will get the error. So, and once we know the error, we add the errors to the first estimate to get the next estimate, and then we will follow these steps to get the next and next and next estimates. So that was basically the conclusion of the lecture. I hope you understood now the Newton-Raphson method and the general form of the Newton-Raphson method. But once again, we will learn this method, we will learn it in a better way by working on exercises. So we will learn this method by working on exercises, and I have now concluded the general form, or I have concluded the discussion on the Newton-Raphson method. So we will learn this method by working on exercises. So with this I conclude this lecture, and we will start the next lecture with the exercise. So I hope you understood the lecture. Thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuh.